Hi, good morning. This chapter, chapter 24, it's about electromagnetic waves and it is mainly talking about Maxwell's equations. It's a very short, brief, chapter, um, and I hope you're gonna enjoy it. Now, there are equations that were brought by Maxwell. We call them Maxwell equations. The first one is talking about the electric field line. And I would say this is a summary for what we did before. Originate on positive charges and terminate on negative charges, like we did for electric field mapping. The electric field is defined as the force per unit charge on a test charge, and the strength of the force is related to the electric constant epsilon zero. Remember these all, like here we define the electric field as force divided by Q. Also, okay, for the electric force, it was depending on a constant, which is K, which is 4 pi epsilon 0, Q1, Q2 over R squared. And from Maxwell's first equation, we obtain a special form of Coulomb's law known as Gauss's law for electricity. Okay, then this is really, and we did talk also about Gauss's law and the idea of the flux. Now, magnetic field lines now, they are continuous. They have no beginning, no ending, because they will be, okay, from the north to the south, outside, and then from inside, they're gonna be from south to north. Then they form closed lines. No magnetic monopoles are known to exist. We cannot have we cannot have a north pole by itself. We cannot have south also. The strength of the magnetic force is related to the magnetic constant mu zero. In all the equations that we provided for a magnetic field, for a wire, for a loop, for a solenoid, all of them, they have a mu zero, which is 4 pi 10 to the negative 7. And this is, we call it permittivity of free space. The second Maxwell equation also can be known as, Gauss's law for magnetism. Again, having the idea of the flux. A changing magnetic field induces an electromagnetic force, and this was the topic for chapter 23, and hence an electric field. The direction of the EMF opposes the change, and that one was Lenz's law. This third of Maxwell is Faraday's law of induction and includes also Lenz's law. Magnetic fields are generated by moving charges or by changing electric field, and this fourth of Maxwell equation encompasses Ampere's law and adds another source of magnetism, changing electric fields. All right, then these are Maxwell equations, and it's very important for us to find now how we can unify the magnetic force and the electric force in one equation. And Maxwell did complete and symmetric theory that shows that the electric and field forces are not separate. They are really, they are the same thing, but they are showing two different faces, which is, they are the same electromagnetic force. And the classical unification of forces is one motivation for current attempts to unify all the four forces in one force, the gravitational force and the electrical force, and also the strong and weak nuclear force. Now, this is showing you here the relationship that is including calculation of c. C here, it's speed of light. And of course, we can use here the value of a mu zero, and the value of epsilon 0 to calculate C, and C is calculated as 310 to the 8 meters per second. This is the ultimate speed of anything, like anything can move faster than light. Now the units here are, you're showing you here that the units are really consistent. This is the 1 over the unit for I will say for mu 0, and this is for epsilon 0. Now this C here, it is coulombs, it's not C speed of light. This is lowercase, and this is uppercase. And you know, the difference is that this is a physical quantity, this is a unit. Okay, this here where we can show that like, you know, the derivation for units from really the force equals BLV equal a Newton, and how we really define the Tesla, and then reaching again the same derivation, like just to show you that the unit that we're gonna have here, it is meters per second, because when I multiply C squared coulomb squared divided by AMT, which is the unit for Newton times meters squared, and this is Tesla times meters divided by ampere, these they're gonna cancel, and here I can reach centimeter second squared divided by meter squared. When I take the square root, it's going to be meters per second. Also, there is another scientist, his name is Hertz, and he observed that when we have this, you know, this circuit here, where we have this was 1887, we can generate, using this device, electromagnetic waves. Here we have a transformer, and the first coil, it is connected to a resistor and a capacitor, and there is an AC source, and the second one, it is connected to this loop 1, and the loop 2 is the receiver. This one is the transmitter, and that one is the receiver. And he was able to use this circuit to generate electromagnetic waves. That is RLC, because it has an inductor, it has a capacitor, it has a resistor, and this caused sparks across a gap in the wire loop, like the first one, which is the loop 1, and generates electromagnetic waves, and the sparks across the gap in the second loop located across the laboratory gave evidence that the waves had been received, okay, by loop 2. This circuit resonates, have that resonance at 1 over 2 pi square root of L over C, and we know that V, it is F times the wavelength. F here stands for frequency, and it is measured in hertz, and lambda, it is wavelength in meters. This is a general equation for waves, and light is a wave, but it's very special that it has C as its speed, and then all the waves travel with C, therefore F is inversely proportional with lambda. Then when I will say red, for example, red is going to be the longest lambda, but is going to be the smallest frequency. What is related also with it is the energy, like it's the lowest energy, the lowest frequency. On the other hand, when I say violet or blue, it has the shortest lambda, and frequency and E, they are going to be the maximum for this visible light. This is showing you the electromagnetic waves sent, how really they have the electric field and the magnetic field. If you look at the blue here, it's the electric field. It is oscillating along the y direction. And B here, the magnetic field, the red lines, they are really oscillating along the z direction. Okay, they are perpendicular to each other, and also they are perpendicular to the direction of propagation, which is really the motion of the wave. We can have a relation for an electromagnetic wave between E, the electric field, and B, the magnetic field, by saying C, it is E divided by B. Again, this one, it is speed of light. What is the maximum strength of B field in an electromagnetic wave that has a maximum E field strength of 1000 volts per meter? It's just a simple application of the equation. B is E over C, 1000 volts per meter divided by 310 to the 8 meters per second. This is going to be 3.33 10 to the negative 6 Teslas. Here's just I'm showing you some of the units just to explain how really the units are really now also we have the electromagnetic spectrum, which was really which is like a whole spectrum that we call it electromagnetic spectrum. It is not only the I will say the visible light. We have radio and TV, microwaves, infrared, visible light, ultraviolet, X-ray, and gamma ray. And here we are explaining how they are really produced and their application, and where we can use them, and the issues. And just one thing that I want you here to know that as we go down like this, then the frequency increases, and also E increases, and the radiation becomes more harmful or danger. Gamma rays can cause cancer and radiation damage. Also, I'm gonna provide in the there is a video that I want you to look, like summarizing all this. It's a song I like always to share with my students, just to show you some important information about radiation. Here showing you the different ranges for the radio waves, microwaves, infrared. Infrared means below red, and that band here, this is the only one that we can see from the EMF. And then we're gonna have UV above violet, and then X-ray and gamma ray. Now also here, 3 rules that apply to electromagnetic waves in general. High frequency electromagnetic waves are more energetic and are able to penetrate than low frequency waves, and this is why gamma is dangerous. High frequency electromagnetic waves can carry more information per unit time than low frequency waves, and the shorter the wave of any electromagnetic wave probe in a material, the smaller the detail it is possible to resolve. Like X-ray, we use it to go deep inside crystals and find something about the crystal. Again, this is a very important equation, C equals F times lambda. And here, just to show you that the wave energy is proportional to the amplitude squared, if it is an electric or magnetic, and the intensity average can be written as C epsilon 0 E 0 squared divided by 2, where C, it is the speed of light, epsilon 0 is the permittivity of the free space, and E0 is the maximum electric field strength. We call it the amplitude. And also we can have the intensity in terms of magnetic field, and this is it's very, like I will say, similar. And one more expression, we can have it in terms of the strength of the electric and the magnetic field, and that is E0 B0 divided by 2 mu 0. Now, here an example: calculate microwave intensities and fields on its highest power setting. A certain microwave oven projects 1 kilowatt of microwaves onto a 30 by 40 centimeter area. What is the intensity in watts per square meter? And calculate the peak electric field strength in these waves, and what is the peak magnetic field strength. The power is given, okay, and remember it's kilowatt. And A, it is can be calculated as 30 times 40, and this is in square centimeters. We need to convert into meters by multiplying by 10 to the negative 4. The intensity is going to be equal power divided by area. And then we will be able, and of course don't forget to convert the kilowatt into watt by 10 to the 3. Now I equals, the intensity equals 2 times I average, because we are looking for the whole intensity, and therefore E0 can be calculated as the square root. This means like it's the square root of I over C epsilon 0. Okay, and we can calculate E0 as 2.51 10 to the 3. And finally, B0 can be calculated as E0 over C. And it is 8.35 10 to the negative 6. Okay, I hope that it's clear. And yeah, it's, as I told you, it's a very short, like 23 is a very long, and this one is a very short. Thank you, and have a great day.